So welcome back. This is our 7th video about Markov chains and hidden Markov models. So in this video we're going to talk about particle filtering. This is a technique for approximate inference. So it's going to be different from everything that we haven't seen so far because all the methods that we talked about were exact methods. So they would give the exact answer. Now we're going to see a method that gives us an approximate answer for our queries. So we haven't seen this term filtering before when we discussed the forward algorithm for the hidden Markov models. So this particle filtering will be an algorithm that does the same job as the forward algorithm does for the hidden Markov models, but in an approximated way. So you should remember that the forward algorithm, it tracks the probability of a variable x over time. So it will give us the probability of xt as time passes. And there are some situations where the size of x, so the number of possible states, is too big. And then it may be too big, for instance, to do exact inference. So we know that the forward algorithm, it has a complexity that is squared in the number of states of x. So it may not be feasible to run exact inference, run the forward algorithm in the case that x is too large. But we can also think about other situations. So, for instance, x may be a continuous variable. In this case, we cannot store x as the way that we are doing using tables. We needed to do something else. And we have not touched this problem yet in this course. And the solution is going to be to use an approximate inference algorithm. So we're going to use this idea of having samples. So a sample is basically one data point, then we're going to track it over time. So instead of representing all possible states and the probability associated to each state, we're going to track those samples over time. And we're going to use the samples to compute the probabilities by counting the frequencies. So the idea is very simple. So just to illustrate the idea, we have here two figures on the top and bottom. Of course, this figure, the number of states is very small because it's just a toy example, but it can help us to illustrate the idea. So we have this table on the top here, and this represents all the possible states that we have in our problem. Let me just erase this so I can better explain the idea. So imagine that we have 9 possible states. So that's going to be like x11 is going to be x12 is going to be x13 and so forth. So each position here is a different state. And we want to track the probability of each state over time. So instead of, let's assume that is a very large number, that is not the case, but instead of tracking those probabilities using the forward algorithm, what we're going to do is to have samples. And those samples we're going to use to calculate some empirical probabilities in order to compute and estimate the probability of each state. So for instance, we can work with 10 particles, 10 samples. So we're going to use the name particle as a synonym for samples. And of course, we need to work with a very large number of particles if you want to have some precise estimates. But in this case, let's suppose that 10 is going to be enough. So we have 10 particles here, and one particle is in this state here, x12. There are 2 particles in this state, x23. There are 2 particles in this state, x32, and there are 5 particles in the state x33. So the probability of each state is going to be the number of particles that we have there over the total number of particles. So I'm going to have 0.1 probability here, 0.2 probability here, 0.2 here, and 0.5 here. So what we're going to keep in memory is just a list of particles. So in this case, it would be something like the position for this particle over here. There's going to be 1, 2, and the position for 2 particles here So I'm going to be 2, 3, and 2, 3 again, because I have 2 particles in this position. I have another 2 particles here, going to be 3, 2, and again 3, 2, and the 5 particles in the position 3, 3. 1, 2, 3, 4, and 5. So that's all we're gonna store in memory. I'm not going to store this because it's too big. I'm also not going to store a map that I'm going to associate each position or each value of my state variable to the particles that are there, because it is also going to be too big. Everything that I'm going to store is a list of particles. And we're going to see how we're going to operate with these particles. But in summary, our algorithm will move the particles into the state in order to change the probabilities and compute the probabilities over time. So it should be clear that the complexity of this algorithm is going to be linear in the number of samples, because everything that we're going to do is to manipulate this list of particles. So it's going to be independent of the size of my my state space. And there are many applications for this. Actually, we're gonna dedicate one entire lecture for this topic when we talk about approximate inference by sampling. And we're gonna see that particle filtering is one algorithm for approximate inference using sampling. But we're going to also see that it's one of the techniques that are used to do robot localization in practice. And we have seen a little bit of this before in this lecture when we discussed a very small and toy example of robot localization. Now we're going to refine this example and make it more real. And remember that particles is just another name for samples. So we can think that our representation for P of X is going to be a list with n particles, our n samples. So we have a list like this one that represents the particles that we have in a state space like this one. And in order to be interesting, the number of particles must be much less than the number of possible states. But remember that the number of particles must be large in order to have good approximations. So the number of states must be also very, very large in order to this application to be interesting. During this lecture, we're going to use this idea here to illustrate the possible states and the number of particles in each state. But remember that we should not use that in the implementation, because if you create in memory a map that's going to associate each possible state to a count of particles, that's going to completely defeat our point, because we don't want to need to represent all possible states in memory. That's going to be too costly. So we're going to use the number of particles with a value x to approximate P of x. So we're going to count and see how many particles we have over the total number of particles for the value x. So as we know that the number of possible states is much larger than the number of particles, we can expect that many x will have probability equal 0. Of course, if we have more particles, we're going to have more accuracy, but we need to keep the number of particles below a certain limit in order to make this approximate inference algorithm feasible. And we started algorithm with all particles with weight equal to 1, and I'm going to change the weight as we operate over the algorithm. Let's see in the next slide. So remember that this particle filtering algorithm is going to do the same job as the forward algorithm does. So the idea will involve 2 steps. One is a transition in time, and the other one is an observation of an emission. So let's start with the transition in time. So let's think about how we're going to implement this. We have, in this example here, a set of particles, and we needed to move each particle according to the transition model. So we're going to do that using sampling. So the idea is very simple. So we know that this position here is x 1, 3. And we need to know the transition probabilities. So let's try if we can figure out how it's going to be. So we can think about this. So the transition probabilities are probabilities in the form of, I'm going to give us the next time step. I'm going to write like this, xt plus 1 given xt. So, but that's going to be too large to express. So what I'm going to do is just show you when xt is equal to x13, right? So specific for this position here. And the idea here is to make the particles to move in this grid in a clockwise manner. So we can think that for this position here, we're going to have a higher probability. So we can think that x23, this conditional probability will be equal to, I don't know, 0.5. And for this position here, that is x33, then going to be a little lower. It's also possible to move to this position here. Let's say that x, that's going to be 22 is equal to 0.2. And also, let's suppose that's possible to move here, x32 is going to be 0.1. So that's all possible transitions that can have from the position x13. Of course, in order to make this work, we have to specify the transition probabilities for every possible value of the variable x. So for each possible state. All right, so if we have these values here, how we can move this green particle? The algorithm is very simple. So it's like to think that we have one entire piece. So that's going to be 1. And I'm going to split that in 0.5 and 0.2. And going to be 0.2. Yeah, the scale is not very good. And this is going to be 0.1. Let's suppose that. Yeah, that's going to be 0.2, like this. So it's 0.5, 0.2, 0.2, and 0.1. So what we're going to do is to use the programming language to give me a random number between 0 and 1. And if this random number is in this range here, that starts from 0 to 0.5, I'm going to move to this position. If the number is between 0.5 and 0.7, that is this limit here, I'm going to move to this position. From 0.7 to 0.9, I'm going to move to this position. And if it's larger than 0.9, I'm going to move to this position here. So in this case, we are moving the particle according to these transition probabilities here. And remember that we need to specify those transition probabilities for every possible state. So this state here will also have its transition probabilities, possibly, I don't know, something to here, to here, to here, and to here, possibly even stay in the same state. That's also possible. And we're going to do this to create this clockwise movement. So if you are in this position, so probably you're going to have transition probabilities for these states here. Okay, and if we have enough samples, we can expect that these samples will mimic the behavior of the transition probabilities. So we're going to be consistent. So we're going to be close to the exact values before and after the transition. Okay, and after we transition in time, we need to make one observation. So we're going to solve this problem of observing evidence with a different technique. Now we're going to downweight the samples based on evidence. So we know that when we are working with the beliefs, as we observe a new belief, we multiply the beliefs by this probability here. Is the probability of the emission given the state x. So I'm going to take this idea and going to weight the particles using the same probability. So each particle is going to receive the probability of the emission given x. So in this example here, we have these particles, and they are disposed in this way here. So we're going to take each particle and weight it based on evidence. And let's suppose that my evidence is the following. We're going to use some sensor that will give us the likely position of the robot And it says that the robot is in this position here, the X2, 3. So all the particles that are in this position will receive a higher probability, but because this sensor is not completely reliable, we're going to also associate smaller probabilities for the older states. So in this case here, all the particles that are here in the state 2, 3, you're going to receive 0.9 probability, so like this one. You're going to associate smaller probabilities for these states here that are just one step away from the stage 2, 3, and I'm going to give them 0.4 probability. This one, you're going to get a 0.2 probability, and this one that is very far away, you're going to get 0.1. Remember that in this situation here, the sum of the weight of the particles was not 1, and in this case here, it's also not 1. So in this case here, we have any particles, and each one is going to have a different weight. That's going to be the probability of E given X. That varies for each particle depending on where the particle is located. So there is one small problem here, is the fact that if we continue this algorithm and continuing sampling and re-weighting particles, the weight of the particles is going to be smaller and smaller over time, and they may vanish. So the way to solve this is using a resample procedure. And this resample procedure will be equivalent to renormalizing the distribution, something that we can do with the forward algorithm. So the idea here is very similar to what we did before with the transition probabilities, that we're going to take the random number generator and we're going to sample a random number from the uniform distribution. It's going to be a little bit more sophisticated now because we have this list of particles that we're going to sample from, and we're going to sum all the weights. I'm going to call this Z, and I'm going to divide each one by Z, right? So I'm going to divide by Z and divide by Z. If we do that, the sum of all those particle weights will be 1. So again, we can use the same idea, that we're going to have this one interval. We can use the random number generator to generate a number between 0 and 1. And if the number that is given to us is between 0 and 0.9 over Z, so we're going to sample this first particle here. And this continues to be like the same, and this is defining all the possible divisions of the 0-1 interval. So every time that we call the random number generator, we're going to sample one particle. So we will need any calls in order to sample any particles. And we're going to do this with replacement. So we can bring the same particle more than once if it is the case. So what we can expect? We can expect that particles that have a very small weight will be not represented, or will be represented by a very small number of particles here. Right? These two particles here that sum a little bit of weight, they have one particle representing here. But these particles here that are the most likely state given the emission will have more particles here. Take a look at that. The green particle is represented by two particles in this state here, because this green particle was sampled twice. And now the algorithm is complete. I'm going to repeat these two steps, actually 3 steps if we count the resample, right? So we're going to be the transition, emission, and resample, and we're going to do these 3 steps over again and again for each passage of time and emission. So this is a small summary of the steps of the algorithm. Just remember that we only keep track of a list of particles. So we start with this list that is represented graphically here, and we do the transition in time. So I'm going to move according to the transition probabilities. In this case, the green particle comes from here to this position here, and I'm going to re-weight according to the mission. So if we observe it that the most likely position of the robot is this position, the particles are here, will receive a higher probability, and the ones that are more distant will receive a smaller and smaller probabilities. And they're going to resample. And when we resample, we will establish the n particles with one weight. That is an important step in order to not lose track of the weight of the particles, because they can become smaller and smaller over time. So we're going to reweight, and we'll continue from the first step here again and do all the steps. So this is one application of particle filters for robot localization. So when I saw this problem for the first time, I thought that it would be very simple to solve, because there are devices that you can install in the wheels of a robot. They're called encoders, and those encoders are very precise. And in this case, it would be very simple to track the position of the robot in a map if you know how much the robot has dislocated in the map. So the idea would be something like this. I have a map, and I have the robot, and the robot is here. It's going to be its first position. And okay, I put the robot there. I can register where is this position, and I know where it is. And I can say, robot, go to the north, I don't know, like 5 meters. And I know that this position here is the same as the first position plus 5 meters. And if I say go to east, I don't know, 10 meters, I know that this position is equal to the previous one plus 10 meters to east. But that is not that simple. Actually, it's a lot more complicated problem. If you keep in doing this, if you keep in summing these positions, the errors are gonna accumulate, and after a few minutes, you think that your robot is here, but actually your robot is there. And so that is not a good way to solve the problem. And the problem of this solution is the fact that even though the encoders are very precise and they tell you how much wheel has turned, when you put the robot on the floor might be slightly slippery, or the robot can touch one obstacle and can stay stuck somewhere, and you think that the robot is moving, but actually it's not. The wheel will turn, but the robot will not move. Or it will move, but they're going to move much less than you expect. So a different way of solving this problem is to use some sensors that can tell you what is the distance to the nearest obstacle. So I have here one animation, and I'm going to show you, and you're going to see how it works, and I'm going to discuss this later on. So we can see we have many particles in the beginning, and these particles are disposed uniformly over the map. But as the robot starts moving, we can see that the number of particles start to accumulate in a few points. And now we have basically two positions. They are the most likely ones. This happens because the map is symmetric. But as the robot enters in this room, we can see that because of the difference between this room and the other one, so for instance, we have this table over here that we don't have here, you can figure out where it is. So just to think about this example and try to make it a little bit more concrete, let's try to think about some possible ways of implementing the transition and the mission probabilities. For the transition probabilities, we can think about something that's very simple. Actually, we can think that the robot, when I command the robot to move, for instance, 1 meter, it can move 1 meter, but also it can move less or more than 1 meter. So we can put something like a Gaussian here. And the variance of this Gaussian will depend on the robot. So robots that are more precise, they will have a smaller variance. Robots that are less precise will have a higher variance. We may think that it will be very rare the occasions that the robot actually have at this location that is higher than what I commanded. But yeah, in this case, we can change the model if we want to. But we can think that, I don't know, possibly the robot can go downwards, and in this case, it can move a little more than what we have commanded. All right, so this is for the transition. So if you have a robot in this position here, after one pass of time, and if we command it to move 1 meter in this direction, we can expect that it will move 1 meter, but it can move a little more than that or a little less than that, and so we can make this model as precise as we want. But the idea here is that when we have the passage in time, what will happen is that we're going to increase our uncertainty about the location of the robot. And we needed to have the mission probabilities too, right? And the mission probability is going to be slightly different. So for instance, we can think about the robot in a certain position. Let's suppose that we have the map is just like this. So I'm going to try to copy this here. And you probably noticed in the animation that we have several lines going different directions, and more or less like this. So what we have is a sort of a LiDAR. So it's going to be a laser radar that measures the distance between the robot in different directions to the nearest object. But this sensor has a little bit of noise, so sometimes it gives us a reading that is more than the obstacle. Sometimes it's going to be less than the distance to the obstacle. So there is some error involved. But we need to compute the probability of the mission given the position. And we have different positions in the map, one position for each particle. So what we're going to do is we're going to simulate, so given the readings, I'm going to simulate the robot in different positions in the map. Again, one for each position that we have a particle, and I'm going to compute what is the error between the readings and the obstacles in the map in the case that the robot was in that position. So let's suppose that, so we have this, we are simulating that the robot is in this position in the map. So in this case, we have this error here, we have this error here, we have a small error here, a small one here, more error here, a small one here, and a small one here. And we sum up, and we have a total error. And we can, for instance, think about the probability distribution of the error given the position, and it should be something like this, and going to vary according to the specifications of the sensor. But we can think that if the error, that's going to be the error here, right? And if the error is small, so we should have a large probability of it being in that position. If the error is large, we should have a very small probability of it being in that position. So we can think about a more concrete example here. Let's suppose that we are comparing two particles, and let's suppose that one particle, so it's exactly the same room, but one particle is more in the middle and the other one more closer to the right to the right wall. So, and we have those readings here from the sensor, and they seem very compatible with a few exceptions here, very compatible with this position here. And if we look at this particle, and with we put the same readings, we're going to see that there will be a large error involved here, something like this, right? So what we are measuring with this probability here is the probability of the mission, that is what is the probability of the reading that we have for each possible position x. For this position here, it's very likely, so this probability is going to be high. For this position here, it's very small because all the errors they're assuming are going to be in the position like this, so the probability is going to be very small. So this particle will receive a smaller weight, and this particle here will receive a larger weight. So great, we got to the end of our lecture about the Markov chains and hidden Markov models, and these are simple examples of dynamic Bayesian networks. So a dynamic Bayesian network is a network that allows us to add nodes in order to model chains over time or space. So we discussed the Markov chains. They are interesting because they allow us to track the probability distribution over a series of transitions in time. For many sequences, the probability distribution converges to a stationary distribution, and the stationary distribution has several applications, such as the algorithms that I'm going to discuss for approximate inference using sampling. We also saw one example, that is the PageRank algorithm, that can be understood as a Markov chain. And the hidden Markov models, they add one more layer of nodes. There are the hidden nodes that allow us to model hidden states in Markov chains. And those hidden states are states that cannot be directly observed, but we can make inference about them using the emission probabilities. So these models are used in different applications, including language and signal processing, as well as the example that we saw in this lecture about robot localization. So, okay, that's all for this lecture, and we see you in the next lecture about Markov networks.